So we can start now. Today's first invited lecture will be delivered by Professor KALYANI from IIT Chennai, and the session will be presided by Dr. Mizanur Rahman. He is a faculty member of the Kazi Nazrul University, West Bengal. So I now request Dr. Mizanur Rahman to take over the session and to proceed.
Okay, thank you, Dr. Naim, and good morning, everyone. It's my pleasure to introduce and welcome our distinguished speaker for today's session, Professor KALYANI from the Department of Mathematics, School of Advanced Sciences, Vellore Institute of Technology, Chennai. Professor Desikan earned her PhD in cosmology from the Indian Institute of Technology, Madras, and has built an impressive academic career over the last 3 decades. At IIT Chennai, she has held several important administrative positions, including Dean Academic Research and Dean School of Advanced Sciences, demonstrating excellence in both leadership and scholarship. Her research interests span a wide array of areas, including spectral and chemical graph theory, cosmology, data clustering, and machine learning. She has guided several PhD scholars and has over 50 research publications in reputed journals, international, national, and international journals. In recognition of her contribution, she has received the Best Faculty Award Female and the CTS Best Faculty Award at IIT Chennai. Today, she will be delivering a talk on the fascinating topic, exploring topological indices in the context of fuzzy graphs. We are delighted to have her with us and look forward to an insightful session. May I now request Professor KALYANI to kindly begin the session. Over to you, ma'am, sir.
So thank you very much for that very warm introduction. Thank you so much. And at the outset, I would like to thank the organizers of this conference for inviting me to deliver this talk, especially Dr. Madhumangal Pal and of course Dr. Balamurgan, who was also instrumental in coordinating this talk. Thank you so much for the organizers once again. With that, I think I will start sharing my screen. And this is just an attempt because my main interests are in spectral graph theory, chemical graph theory, and we are working on machine learning algorithms using graphs. And this particular conference has motivated me or inspired me to look into aspects of fuzzy graphs as well. So thanks to the organizers for helping me to explore one more area. So thank you so much for that. And definitely, I think this would be an introductory session. And more specifically, I think it would be of interest to young researchers who may be looking to find some new research areas. Okay, so with that, I will share my screen. And if there is an interruption, please do not hesitate to interrupt me and tell me that I'm out of line or got disconnected or something like that. Okay, so thank you so much. I think I will turn off my video because there is some minor issue in my video. I'll turn off my video and then I would share my screen. Yes, I think my screen is shared, sir.
Yes, yes.
Yeah. Yes. Thank you very much. I would be presenting my lecture on exploring topological indices in the context of fuzzy graphs. But as I already mentioned, our research group's focus is on topological indices applied to just graphs. But this has, truly inspired me to look into topological indices in the context of fuzzy graphs. Okay, so this would be the brief outline of the talk that I would be presenting today. So we'll be just looking at what are graphs and what are fuzzy graphs. This is mainly for the young researchers who have joined this online platform. And then we'll be looking at what are the applications which are possible from fuzzy graphs, and of course the types of fuzzy graphs. We would not be looking at all the types of fuzzy graphs, just a few of them, just to give an indication of the various possibilities which are there. And of course, I would be formally defining what is a fuzzy graph, And then we'll be looking at specifically one simple fuzzy graph, which is the fuzzy cycle graph C4, so that we can illustrate how the topological indices are going to be computed with respect to this very simple graph. This is just for illustration purpose. Definitely, for any application, this can be extrapolated and we can work on it. Okay. And then, as I mentioned, the focus would be on topological indices, and we'll be looking at a very brief history of topological indices and where topological indices are applied. And then we'll be looking at a few types of topological indices. And in today's talk, I would be mainly concentrating only on degree-based topological indices. And of course, the core concept out here, which is the core concept of the talk, is topological indices in fuzzy graphs. And the indices are going to be computed for the fuzzy cycle graph C4, and the key references which have been made use of. So this is a broad outline of today's talk. Having said that, let me move on to graphs. Okay, so graphs, as we all know, it is a representation of anything in the real world which are discrete in nature. Okay, so when we have discrete objects and there is a relationship between the objects, we could represent it as a graph. And we know that each of the discrete objects are going to be denoted as vertices or nodes, and two different entities or objects are going to be connected or related through what is known as an edge. Okay, so this is a basic representation of a graph, which all of us are familiar with. So any scenario where we have discrete objects and relationships with them, it can be represented as a graph. So any real life phenomena where we can associate relationships can be represented as a graph, and this is very well known to us. But these graphs are not sufficient in themselves, because the graphs that we have been talking about in the so-called the traditional graph theory, they do not capture the uncertainty. So there comes the concept of fuzzy graphs. And fuzzy graphs were first introduced by Kaufman in 1973 based on Zadeh's fuzzy relation. So this was the first. In 1973, Kaufman introduced the very first fuzzy graph. And in today's discussion, I'll be sticking only to the basic fuzzy graph, and I would not be venturing into the various varieties of fuzzy graphs which are there. So this is just as a beginner's guide to topological indices in fuzzy graphs. Right. So now, as I mentioned, fuzzy graph theory is growing rapidly, or has been growing very, very rapidly over the years since it was introduced by Kaufman, and it finds various applications in, say, network theory, communication, data mining, clustering, image segmentation, planning, and many more areas. Okay, these are just a few of the areas which have been listed out here. So it finds its application in various areas, and among this, today we'll be applying the topological indices to fuzzy graphs. Now, the different types of fuzzy graphs, again, this is only a very limited list which I'm presenting. This is not an exhaustive list of fuzzy graphs which are available. And the types of fuzzy graphs include the original fuzzy graph introduced by Kaufman. And then, of course, we have the intuitionistic fuzzy graph, which was introduced in the year 2000. And then we have bipolar fuzzy graph, which was introduced in the year 2011. And interval valued fuzzy graph introduced again in 2011. Pythagorean fuzzy graph in 2018. And there are many more. So varieties. And just as from the application perspective, I've just mentioned fuzzy tolerance graph, fuzzy competition graph, and so on. So this is mainly to enthuse young learners who may want to find their research areas in any of these domains, or apply their whatever concepts they have to these types of graphs. So this is just what are the types of fuzzy graphs that are available. Now, going into a little more detail, we're just starting off with the basic fuzzy graph. This is the most basic form. And the normal graph that we are talking about under graph theory, we can, because we have moved into the concept of fuzzy graph, we can call those graphs as crisp graphs. And that is the most, so opposed to the crisp graphs, we have the fuzzy graphs, which are going to take uncertainty into consideration. So that these are the fuzzy graphs which were originally introduced by Kaufman. So this is the most basic form of the graph where we associate what are known as membership values with to both the vertices and the edges. So the uncertainty is captured using these membership values, and the value itself represents the strength of the relationship. So both the vertices and the edges are going to be assigned membership values. And from this grew the next variety of fuzzy graphs known as the intuitionistic fuzzy graphs, where not only membership but also non-membership is also taken into account. So both the vertices and the edges are going to be assigned membership as well as non-membership values. So moving further, we have bipolar fuzzy graphs, which gives us much more flexibility compared to probably the basic fuzzy graphs that we have. So this can take into account, because we can understand from the word bipolar. So we're going to take both positive and negative degrees of membership into account. So this gives us a much more broader range of applications that we can work with. And from I think bipolar, we have other varieties of M polar and other varieties of fuzzy graphs have evolved from the bipolar fuzzy graphs. And of course, we have the interval valued fuzzy graphs as well, where in the intuitionistic, we just have single membership and non-membership values assigned to the vertices and edges. Here it is, instead of single values, we have intervals which are assigned to associate membership and non-membership values for both the vertices and edges. And moving further, we have the Pythagorean fuzzy graphs. Here, along with the vertices and edges having membership and both non-membership values, they also satisfy the condition that individually for the vertices and as well as for the edges, the squares of the membership and non-membership values, it will be less than or equal to 1. So these are some basic varieties of fuzzy graphs which are available. And as I mentioned, there are many more varieties of fuzzy graphs, and we have experts here like Dr. Pal as well, who have they are experts in fuzzy graphs. So there is a book as well by them, which I will come to towards the end. So there are a lot of experts who have typically worked on fuzzy graphs who are in this online platform right now. So moving further, so let's formally define the fuzzy graph. As I mentioned, this fuzzy graph that I'm going to deal with today is only the basic type of fuzzy graph which was introduced by Kaufman. This is just for illustration purpose. We are going to stick to that. Okay. So fuzzy graph is where every vertex and edge is going to be assigned a membership value, and this membership value, as we know, it lies between 0 and 1. Right. So this value, it represents the degree of uncertainty that we are associating with the vertex or with the edge. So formally, we can define a fuzzy graph G tilde as the pair V tilde E tilde, where V tilde is the fuzzy vertex set, and every vertex in this vertex set has an associated membership value. So it's a mapping from the set of vertices to the closed interval 0, 1. Similarly, we have the fuzzy edge set denoted as E tilde, and where each, and one more thing I would like to stress on is all the graphs that we are considering in today's discussion are undirected graphs, and they are all simple graphs in the sense we don't have multiple edges and neither do we have loops. Right. So each unordered pair, UV, we associate a fuzzy membership value. So it is a mapping from V cross V to the closed interval 0, 1. And there is a condition that between any two vertices U and V, there is an edge, and the membership value of that particular edge, that is mu of U comma V, that is the membership value of the edge connecting U and V, will always be less than or equal to the minimum of the membership values of the end vertices. Okay, so you have the edge UV. So the membership value of the edge connecting U and V, that value will always be less than or equal to the minimum of the membership value of U, minimum among the membership values of U and V. This is true for all the edges. So this is the constraint that we have when we are talking about a fuzzy graph with respect to the membership values of the vertices and the edges. So now let us look at an example, and this is the graph that I said that we are going to make use of throughout. So this is, all of us know that the cycle graph C4. But only thing is we are looking at a fuzzy cycle graph C4. So we have the vertices V1, V2, V3, and V4. And obviously it's a cycle, and we have 4 edges connecting the vertices V1 to V2, V3, and V4 back to V1. So now if you look at it, each of the nodes or the vertices, they are assigned membership values. So the vertex V1 is assigned the membership value 0.9. Sorry, there's a typo here, just not comma, it has to be 0.1. Sorry, 0.9. So the vertex V1 has the membership value 0.9, and the vertex V2 has the membership value 0.8, and so on. And you can see that the edges also have the membership values assigned to them. And you can see that the membership value of the edge V1 and V2 is 0.8. And it does satisfy the criteria that I had already mentioned. The membership value of the edge must be less than or equal to the minimum of the membership values of the end vertices. So the end vertex value here is 0.9, and here it is 0.8. And obviously here it is 0.8, which corresponds to the minimum of the membership values corresponding to V1 and V2. Okay, so similarly, all the edges have their associated membership values. So this is just an illustration of a very simple fuzzy graph. This is, again, I'm reiterating the fact that this is purely for first timers who are looking into fuzzy graphs and the application in topological indices, and anybody who wants to venture into this. Right. Now, once again, when we come to this fuzzy graph, we have to, the moment we talk about a graph, we have to understand what do we mean by degree of a vertex, right? And here we are going to define the fuzzy degree of a vertex V. It is nothing but the sum of the membership values of the edges which are incident on a particular vertex. Okay, so if, for example, we'll directly jump into the fuzzy cycle graph C4 that we have. So we have the vertex V1, okay, and we have 2 edges incident on it. We have the edge V1, V2, which is incident on it. Again, we have the edge V1, V4, which is incident on it. So the degree of this particular vertex V1 is sum of the membership values of the edges which are incident on it. So the membership value of this edge V1, V2 is 0.8, and the membership value of the edge V1, V4 is 0.85. So when we sum up both of them, 0.8 plus 0.85, we get 1.65. That is the degree of the vertex V1. Okay, so every vertex has an associated degree as well as membership. Okay, so these two are 2 distinct entities that we have. So we have a degree of a vertex and the membership of a vertex. Similarly, we can compute the degree of all other vertices. Again, for V2, it will be sum of 0.8 plus 0.7. So that adds up to 1.5, and so on. So this is how the degree of a vertex is going to be connected. Because in the topological indices that we are going to discuss, we are going to look at indices and degree-based topological indices. So degree is important. So that is why I am reiterating on this particular concept. Now moving further, so you can see that again, I've just summarized both the membership values for each of the vertices and the degrees of the vertices. Okay, so the membership values are assigned and degree is obtained by adding the sum of the membership values of the edges which are incident on that particular vertex. Right. So this is again a very simple example. Okay, so it is, as I said, the main focus of people who want to venture into applications could be something like social network analysis. So it can be modeled using a fuzzy graph is what I would like to iterate. Okay, so this is just a toy network where you have just 4 users or of the network. So you have V1, V2, V3, and V4. You can consider V1, V2, V3, and V4 to be the users. And the 0.1 assigned to V1, 0.3, 0.2, and 0.4 assigned to the different vertices. They may indicate the level of how active the user is in the network. Okay, it may represent the level of how active he is on the network. Okay, so the membership value may be associated with that. Similarly, if there is an edge between these two, it shows that these 2 users are related in some way, and the membership value of the edge, corresponding edge, can be related to the strength of the relation between the users. Okay, so if there is an edge between the 2, there is the 2 are connected on the network, and the membership value purely indicates the level of relation between the users. Okay, this is just a very, very simple toy example that we have here. It's just as an illustration to show that we can apply all this in social network analysis. All right. Now moving on to topological indices, because the main focus is going to be fuzzy graphs and topological indices. Okay. And I think most of us would be familiar that topological indices they're just numerical descriptors that is going to capture the structural properties of graphs. So by structural property, we are just insisting on the fact that if I know the vertices and the edges in the graph, that alone would suffice for me to arrive at these topological indices, and it is a single number which is going to represent that entire graph. And this has found a huge lot of applications in chemistry and in computer science. Okay, the topological indices have found a lot of applications in these two areas. And these numbers, they are invariant in the sense that if I change the labeling in my graph, my numerical value of the topological index would not change. So it is an invariant. So it is a very important aspect that we can make use of. So the labeling is not going to affect my topological index. And again, as I mentioned, it is widely used to work with molecular graphs, biological networks, even social networks, and so on and so forth. So it has a wide range of applications. Now, coming to the history of topological indices, it was first introduced by Wiener in the 1940s, and he introduced the Wiener index. And we'll come to the types of topological indices. The Wiener index falls under the class of distance-based topological indices, and it was used by Wiener to predict the boiling point of alkanes. And from then on, there have been numerous types of topological indices which have been put forth. We have the Randic index, Zagreb index, Balaban index, and so on. Okay, I've just mentioned a few in no particular order or no particular importance. Okay, so I just mentioned a few of them, and there are many more which are being proposed by various researchers around the globe, right? And they are why are they? Why is there a boom of topological index? Or probably I could say it is also reaching a saturation point because people wanted to understand more and more complex molecular structures or graph structures. So each one started proposing plenty of topological indices depending on the scope of their work. Now, again, the topological indices, it finds a lot of applications, as I mentioned, in chemical graph theory, especially with respect to QSAR stands for quantitative structure activity relation, and QSPR stands for quantitative structure property relationship, structure property and structure activity relationship studies. These are very, very important when it comes to drug design, drug discovery, and so on. And again, it is used in network analysis and how to characterize networks. And of course, biological applications, you can look at protein structures, protein-protein interaction. All these can be modeled using topological indices. So they have huge applications. So many of the researchers are working on these areas. So now there are various types, as I mentioned. You have degree-based indices, distance-based indices, degree distance, eccentricity based, eigenvalue based, and so on. Again, no particular order, no particular importance. I've just mentioned a few of them. There are various varieties associated with the topological indices. These are just a few of the topological indices which I have illustrated here. Now, so the few of the indices which we are going to make use of in today's discussion are the first Zagreb index, the second Zagreb index, forgotten index, ABC index, the GA index. Okay, GA index is nothing but the geometric arithmetic mean index. ABC is atom bond connectivity index. These are the respective formula. This is in the usual graph theoretic terms. Here, degree just stands for the degree of the vertex, and so on. So these formulae that we have here for the Zagreb index, the forgotten index, ABC index, GA index, and so on, they're going to be slightly modified when it comes to the fuzzy graphs. Okay, so these are the formulae which are originally there as part of topological indices. When we compute these indices, these are the original formulae. Okay, so here is degree of vertex, and here it is the product of the degrees, and so on. So just a few of them I have listed here. We are going to see how these are going to be modified in the context of fuzzy graphs. And again, we have distance-based indices, Wiener index, hypervenix, eigenvalue-based indices, and we have other varieties of indices as well. Right. So now we are getting into the main topic, okay, and it'll just be an introduction to the topological indices and fuzzy graphs, okay. So and right now we saw that in fuzzy graphs the degrees and distances, they are all based on the fuzzy membership values, right? So the indices, we have to generalize these indices that we have in the normal context where we don't take we don't consider graphs to be fuzzy graphs, rather we consider them to be crisp graphs, we have the formula. We have to extrapolate them to include the fuzziness. Okay, so that is the whole concept of extrapolating or generalizing these indices, right? As an example, the fuzzy Fuzz-Zagreb index, okay, it was modified, it was originally proposed by Kalatian et al. In 2020, where the Fuzz-Zagreb index, this is the Fuzz-Zagreb index, as you can see, it is nothing but the sum of the squares of the degrees of the vertices. So that has been modified as you can see that it is the square of the vertices multiplied by the membership value of the particular vertex. So this is a change which comes into the computation of the Zagreb index when we are considering fuzzy graphs. Okay, so instead of just summing up the degrees, so summing up the squares of the degrees, it is whenever we consider every vertex, we have to multiply it with the membership value of that particular vertex and then sum it up. Okay, so that is going to be the change. So at every instance, we make use of the membership value, be it the vertex or the edge. So that is going to be the overall thing, right? So now let us go back to the cycle C4 that I already gave with the respective membership values for the vertices and edges. And if you're computing the fuzzy Fuzz-Zagreb index for this particular graph, the formula just now I mentioned. Okay, so if we have to compute this entire index, right? So we have 4 vertices. So V1, V2, V3, V4. Supposing I'm considering vertex V1. Okay, if we consider vertex V1, so we have to take into consideration its membership value. So it is 0.9. You can follow my cursor. So it is 0.9 is the membership value of that particular vertex multiplied by the sum of the squares of the degree of the vertex. And we know that the sum of the squares of the degree, the degree of this particular vertex is nothing but the sum of the membership values of the 2 edges which are incident. So the degree of this particular vertex is 1.65, as we have already seen. We have to just square it. Okay. So similarly, we have to compute for all other vertices, taking into consideration the fuzzy degree of the vertex and the fuzzy membership value of that particular index. So this is how the computation is going to go on. So when we complete the computation, we'll be arriving at this particular value. Similarly, if I'm looking at the fuzzy second Zagreb index, okay, the original formula, we saw that it was just the product of the degrees of the end vertices of a degree. Now this is summation over all edges in that particular graph. Okay, so this is all the edges in the graph we need to take into consideration. So here originally, if it is a crisp graph, we just have to take the product of the degrees of the end vertices and then sum up over all edges in the graph. Okay, now we have an additional concept which has come up here, which is nothing but for every edge we need to take not only the fuzzy degrees of the end vertices, which is degree of u into degree of v. Along with that, we need to take into account the membership value of the edge which is connecting the membership value of the particular edge. Okay. So for example, just one I would say, if I want to find out the fuzzy Zagreb index, again, this is over sum over all edges which are there in the graph. So we have 4 edges. So it is 1, 2, 3, 4. For all the edges, we need to take into consideration. So if I'm taking this edge V1, V2, so its membership value is 0.8. I need to take 0.8 into account. So my mu sub b of u comma v for this particular edge will be 0.8. And degree of u is nothing but degree of V1. Degree of V1 is 1.65 into degree of v, the end vertex v2. So that degree is 0.8 into 0.7. So that is 1.5. So it is 1.5 into 1.65 into 0.9. So that would turn out to be 1.98. Similarly, we need to compute the values for all of the edges and then sum up over all edges. We're going to get the fuzzy second Zagreb index. Okay. So I think it's a very neat concept where we have taken the uncertainty into account. Then we are looking at both the membership values of the edges and the vertices. Similarly, the fuzzy forgotten index and so on. Okay, I'm not going to repeat it. Okay, so we can just see that this is sum over all vertices. So when we are doing this, we have to take the cube of the degrees. And whenever we say degree now, it is nothing but the fuzzy degree of the vertex along with the membership value of that particular vertex. So like that, we can compute the fuzzy forgotten index, fuzzy inverse degree index. Okay. So at every point, we just need to incorporate the fuzziness in the graph and make use of the membership value and the appropriate fuzzy degree of the particular vertex. This is the fuzzy. So we can compute the fuzzy forgotten index, fuzzy inverse degree index, atom bond connectivity index, right? Fuzzy geometric arithmetic index. So these are just, just to show that how the normal concept of topological indices can be extended to fuzzy graphs. Okay, so these are a few of the indices, and again, Randic index. So all these are just computed. We just need to take into account the appropriate membership values and the corresponding degrees and substitute into the formula, and correspondingly we can get the index values. Okay, so we have seen quite a lot of indices as of now: first Zagreb index, second Zagreb index, how to compute the forgotten index, how to compute the inverse degree index, how to compute the ABC, which is the atom bond connectivity index, geometric arithmetic index, Randic index, harmonic index. Okay, and this is just an illustration of one of the distance-based indices, which is the Wiener index. Okay, so Wiener index for the fuzzy context is defined as mu of Vi into mu of Vj, which is the membership values of Vi and Vj of that particular edge. And this d of Vi comma Vj is nothing but the distance between Vi and Vj. Okay, so now this distance is nothing but the shortest path distance of the graph. Okay, so here when you're computing the distance, distance is only with respect to the presence of the edge, not with respect to the membership value. That alone we need to take into account. Okay, if there is an edge, okay, so it is computing the distance alone would correspond to something like what we do in a crisp graph. Okay, so other than that, when we're computing the Wiener index, we can take the product of the forgotten of the membership values of the n vertices of the edges that we have. Right. So if you look at this, we know from the graph, it is a cycle graph, we know, and these distances are purely based on the just the presence of edges. So we know that distance between V1, V2, all these things are 1, 1, 1, shortest path distances, and between V1 and V3, it is 2 edges are there, so it is 2. Again, between V2 and V4, the 2 edges are there, so it is 2. So once we have these values and the membership values of the vertices are of course known, based on that we can get the fuzzy Wiener index of this particular graph. Okay, so that's what is given here. Shortest path distances are plugged in, and now we just all the shortest path distances are plugged into this particular formula, and then we just need to make use of the membership values of the n vertices, and then we can go ahead and compute the Wiener index for the fuzzy cycle graph C4. Right. Similarly, we can do the same thing with respect to the hyper-Wiener index, where along with the normal distance, it is the sum of the distance plus the square of the distances between the vertices that we have here. So this needs to be taken into account. So we can compute the hyper-Wiener index as well. Right. So this is just a summary of all the topological indices that have been computed for the fuzzy cycle graph. Based on that is, again, I'm reiterating, it is only the basic fuzzy graph that we have taken into consideration. All these can be extrapolated into the other formats like intuitionistic fuzzy and so on, depending on our requirement. Okay, so this is just a summary of all the indices that have been computed. Right, so this is just to give a feel of how topological indices can be extended to fuzzy graphs. Right, so now I'm just coming towards the end of my discussion, and I've given just a few of the things which where fuzzy graphs can be applied: network analysis and decision making. Again, I'm not saying that this is an exhaustive list. Okay, so these are a few things where we can make use of in transportation planning or any other applications. You can see there are quite a lot of papers which are available. I've listed just a few of them here. This is purely only for network analysis and decision making. We can look at other applications as well. Right. So these are just a few of them, again, only in network analysis and decision making. Right. So my idea was just to give all an overview of how topological indices can be applied, and of course you can extrapolate it and use it. Topological indices as well can be applied to network analysis. Okay, so that is one more area which I'm personally inclined towards taking up now. And these are some few key references, and and these books are something which I've gone through, right? So this is the original paper by Kaufman, and of course this is a book, Fuzzy Graphs and Fuzzy Hypergraphs, and of course this is also a book, Fuzzy Graph Theory, and this book, Modern Trends in Fuzzy Graph Theory by Dr. Paul and his collaborators. Okay, so these are some standard books which have been referred while preparing for this, because as I mentioned, my interest in this is new. Okay, so I definitely need to explore a lot more. So thank you very much for the opportunity. Thanks a lot.
Thank you, madam, for your excellent delivery. Now, this is the time for question session. If there is any question from the audience, you can ask now.
So shall I stop
Any?
present? Shall I stop my presentation, sir?
Okay, ma'am.
Good morning, madam.
Yes, ma'am.
Madam, your lecture was so interesting, and we have known, say we were able to understand most of the basic things related to topological indices. Madam, I have one doubt related to that.
Yes. Yes,
It's
please.
given in the definition that from the topological indices, we will be able to understand almost everything related to fuzzy graph.
Not
So,
everything related to fuzzy graph, ma'am. What I'm saying
uh,
is topological indices are numerical descriptors of a particular graph. Okay, till now,
okay,
what I have seen is topological indices have been applied to crisp graphs. Okay, so where there's no fuzziness, people have
okay,
employed
okay,
various topological indices. So that will be a number, and they will start associating it with various properties of the graph. Okay. Now, this
okay,
particular thing, what I'm trying to say is for fuzzy graphs as well, you can compute topological indices, but you just need to take into account the membership values of the vertices and the edges. Just an
okay, ma'am.
extrapolation of the usual topological index.
Okay. So using this fuzzy topological index,
Yeah.
it has your trying to say that it has lot of application, but
Yes.
for the time being that you are just introducing that, and we need to read more on that.
Yeah, it has already been introduced. I'm just trying to do it for one class of graph, that is the cycle graphs. But I'm saying that
Okay.
you can apply it. Especially, I found a lot of applications probably now. I don't think whether it will be applied in chemistry, but maybe we can apply it to social network. That is why I introduced a toy example of a social network. Okay, so where we
Okay.
can make use of these topological indices to analyze networks, do clustering in the networks. A lot of things can be done in network analysis.
Thank you, madam. Thank you very much. Thank you,
Yeah,
madam.
yeah. Thanks a lot, ma'am.
May I just make
So
a comment? I am
good
from
morning, ma'am.
Yes, sir.
uh, just one thing that uh, the first research scholar who worked with me was Mimi Dash. She
Yes, sir.
submitted her thesis sometimes in the middle of the 80s, and the thesis was on.
Excuse me, sir.
Sorry.
Sir, your sound is very slow. Kindly-
So let me. Okay. Do you hear me now? Better.
Yes, sir. Yes,
yes,
sir.
yes,
Yes,
sir.
sir.
Okay. Okay. Uh, my first research scholar was Mili Dash, and
Okay, sir.
she submitted her thesis in sometimes in mid 80s, and it was on fuzzy relations on fuzzy sets and fuzzy graphs and hypergraphs.
Yes, sir.
So almost that is not mentioned anywhere. Uh,
Sir,
there
yes,
are
sir. Sorry, sir. No. I just mentioned that I did not give the exhaustive list of references.
no.
Yeah.
I don't just I'm not talking about your presentation only, but in general it is true. So I would request everybody here to just look into those some of those papers.
Definitely.
I think that the initial papers were published in fuzzy sets and systems in 80s, late 80s.
Yes,
So
sir.
you can just check. That's all.
Definitely, sir.
Thank you very much.
Definitely, sir.
Okay, if there is any other question from the audience.
Ma'am, I have a doubt. Ma'am, when you showed the formula for the first Zagreb index for fuzzy graph, it's shown as summation over a set of all vertices, uh, multiplying the degree of membership of the vertex into that degree of the vertex, right?
Yes, ma'am.
Ma'am,
Sum of square of the degrees.
yeah, square of the degree. So when I went
Yeah.
to refer some papers, in some papers it's shown that we multiply the membership value of the vertex into the degree and we square it together.
Yes,
Is
ma'am.
it
Yes,
correct,
ma'am.
ma'am?
This correct. No, no, like I mentioned that this definition is like Kalatian and et al. Okay, they have in their paper they have mentioned it like this.
Okay, so we can
So that,
define it in different ways.
yeah. What you are mentioning is membership into degree. Take that and square it. Correct.
Yes.
Okay. Yes, because even I saw different varieties. That is why specifically I mentioned Kalatian's paper.
Okay, ma'am. Thank you, ma'am.
Yeah.
Probably instead of using the same name, we may use for different names for different types of definitions rather
That's
than
a
the
definition.
diagram.
No, no, that is why I just put Kalatian. K was there in the formula. Okay, this confusion was there. So even I got confused. So I specifically took this one definition. But what being told right now by madam is also correct. In some papers, we find the membership into degree. Take that and square it.
Correct.
Okay, I think there is
Good
no
morning,
question.
ma'am.
Yes, please.
Ma'am, is there any condition to define topological indices, or we can just construct our own topological indices without any
No,
consideration?
no. Normally, topological indices are considered either based on degree or on distance or some combination. Okay, but not all indices would be working fine. Okay, again, we cannot just compute the indices. If you are giving it for an application, those indices should lead to I mean predicting the properties correctly. If they are not being predicted properly, that index is not suitable for that particular class of graphs. Okay, so you have to be careful about defining the indices and using the indices.
Ma'am, one more question.
Yeah.
So when we are extracting the graph from the molecular structure, we are getting a crisp graph. Is there any possibilities to get directly the fuzzy graph from the molecular
No,
structure?
that's what I just mentioned. I don't know in molecular graph whether we can associate fuzziness with the atoms. Okay, so that is why I think I'm not too sure of extrapolating it to chemical graph theory, but definitely for social network analysis and anywhere where you want to look at citation network or any other network, no, there we can apply this concept, I guess. Okay, but I'm yet to explore. I'll get back.
All right, I think we are running out of time, and on behalf of the organizing committee, I sincerely thank you for taking time to share your expertise with us today, ma'am. And
Thank you very
thank you
much.
for your good
But
session.
thank you for the opportunity. I should be thankful to all of you. Thank you so much.
Okay, so this is the end of today's first session, and now that's fine, sir. Thanks a lot to you.
Okay. Thank you, Kalyani ma'am and Nizam Rahman sir. Our
Thank you very
next
much.
speaker is Professor Manish Chakraborty.
Excuse me, sir. One last question.
Yes.
So,
This to
just
this is
ask
for
Francis, you are VIT student. You can meet ma'am in the campus. You can clarify it. Okay.
no. I want to ask from Sir Madhumangalka.
Okay,
Yes.
Francis, okay, you can meet me later. So to sir, you can ask.
Sir, one of your paper that is independent degree of fuzzy. One paper there you have mentioned when the bond is forming between two atoms, there exists a fuzziness. So can you explain about that?
That one basically see that in the chemistry. So there is a possibility for the uncertainty in the energy. It's for non-expression of energy. So there is a scope for uncertainty. Okay. So in that case, we can define the topological indices, or we can define it.
Okay, thank you, sir.
So thank you very much, sir. Shall I leave the meeting now?
Yes.
Yes.
Yeah.
Yes. Yes.
Thank you so much.
So 1 minute,
Okay, so
ma'am. From the society, Sridhar Acharya Academy of Mathematical Sciences, is very pleased and we are honored to present outstanding researcher award to you. So
Thank you so much. I'm honored.
I am showing the certificate.
Okay.
This is your certificate.
Thank you so much, sir. Thank you so much.
So
Congratulations, ma'am.
for
Thank you.
your groundbreaking research work on fuzzy logic and fuzzy graph theory,
Thank you so much.
especially on your fuzzy network programming, etc.
congratulations.
So we are
Thank you.
requesting you to accept our your outstanding research award.
Thank you, sir. I'm very honored to accept this award. I'm truly indebted to the Sridharacharya Academy of Mathematical Sciences. Thank you so much. Thanks a lot.
Congratulations, ma'am.
Thank you so much. Thanks a lot. I'm honored. Thank you, sir.
Congrats, ma'am.
Thank you, sir. Thank you so much.
Okay, so now is the time for the second lecture. It will be delivered